Hello, everyone. Welcome to a special edition of SETI Live with LaserSETI live in Puerto Rico. My name is Lauren Sgro. I am a postdoc at the SETI Institute, and I'm the outreach manager for LaserSETI. And I'm joined here today by Dr. Abel Méndez. He is a professor at the University of Puerto Rico at Arecibo. He's a planetary astrobiologist, and he's the director of the Planetary Habitability Laboratory at the University of Puerto Rico, Arecibo. So many things. Welcome, Abel.
Yeah.
I'm so glad that you are here today with us. And just a little bit about the fact that we're in Puerto Rico, of all wonderful places on this planet. We're here because of LaserSETI. So do you want to tell us a little bit more about exactly where in Puerto Rico we are today?
Yes, we are in Isla Magueyes, Puerto Rico. This is a small island and islet of Puerto Rico. This is part of the University of Puerto Rico, Mayagüez, part of the Department of Marine Science. This is a laboratory. It has a wonderful marine science department, but I should explain later on what's the relation SETI marine science.
Exactly. All right. Thank you so much. And speaking of this beautiful island that we are on today, we actually have a live stream from the rooftop where our LaserSETI instruments have been installed yesterday by the entire team, which we'll tell you about here in a second. But I want to show you really quickly, just so that you can get an idea of the beautiful location where we are at today. You can see the hills in the background, the water, it's beautiful. This is just a really, really short boat ride away from mainland Puerto Rico, and you can see our 3 LaserSETI instruments right up there.
Yeah, that's a nice view, a sunny day. Wonderful.
Yes, we installed them on a sunny day, and that was really fun and really hot. It's a little bit cloudy now. But yeah, we have 3 new LaserSETI instruments. So let me get into that really quickly.
Well, actually, you see it's sunny. It's not sunny, it's cloudy because that's Puerto Rico in the background.
Yeah.
But looking up, this island is special.
Exactly. And that was actually one of the main reasons why this was chosen as the next LaserSETI location. So I'm going to ask you about that here in just a second. But I want to just say hello to everyone that's watching today. We're here live from the Marine Sciences Department and a little bit of a lab. So you'll see some fun stuff behind us. It's a lab, it's a kitchen, it's a multi-purpose room. But we've got our LaserSETI instruments on the rooftop, and I want to say hi to everybody who's watching here. Hello, everyone from Brazil. We've got people from here in Puerto Rico, from Sweden, from Bulgaria. Welcome. There's people all around the world watching. So a little bit more about LaserSETI. So in case you don't know or haven't been following along, LaserSETI is an all the sky, all the time survey looking for optical laser pulses from potentially extraterrestrial signals or from new science. So the idea behind this is that there's not anything that we really know about that can produce optical laser pulses. So essentially, if we find a laser pulse with our LaserSETI instruments, then that tells us that there's some new science to be discovered, or we may be detecting an extraterrestrial signal. And we're installing these instruments all over the world. Puerto Rico is the 4th installation of LaserSETI. And you can see here we have 3 instruments. And those are actually going to overlap fields of view with our previous and future observatories that we are installing. So we've got an observatory in California, one in Hawaii at Haleakala. We also have one in Sedona, Arizona, and this is the 4th. So these instruments that we've installed with the Astronomical Society of the Caribbean, as well as some of your students, as well as with the help of the Department of Marine Sciences here in Puerto Rico, these 3 instruments are going to overlap with our Sedona field of view, as well as our future observatories, hopefully in the Canary Islands. So with these instruments, we're seeing about 30 to 40% of the sky in our survey for laser pulses. So that's our brief intro on LaserSETI. But again, we now have LaserSETI instruments here in Puerto Rico, and Abel really helped us to find this really special location. So do you want to tell us a little bit more about your involvement and how this came to be?
Yes, about 1 year ago, the SETI Institute, via Fran Marches, asked us about the opportunity of having a LaserSETI in Puerto Rico. They were looking everywhere in the Caribbean. So I definitely say, yes, Puerto Rico is a nice place for us for having, and the legacy of the Arecibo Observatory, search for extraterrestrial signals, astronomy, that was very important for us. But the problem was that the island is a tropical island with a difficult weather to predict, especially in the north. So I wish the telescope was on top of my university campus, which is close to Arecibo. But that weather there is not good for optical observations, good for radio, but not for optical observations. So we look through the island, and we have in our island the mountains that cross the island, and that changed a little bit of the weather. And the weather in the south is more drier, and you can see the vegetation. And so we looked through the south where we can put it, and we wanted to put it in one of the UPR system campus. There's 11 University of Puerto Rico campuses through the island. There was one in the south. It's called Ponce, in Ponce. That's that town. But the problem with that was that there was too many illumination, contamination, and then so the other target is this island, Magallanes. The UPR Mayagüez have campuses in the west, which has the problem of too much rain, too much cloud cover. But they have this island. It's a laboratory island, so many research about the marine science are started from this island. So we decided to do it here, and I kindly asked the Marine Science Department director if we can have this optical astronomical instrument here. And he said, yes, that definitely. So we were happy, and we have been in contact, and we have the help of the different UPR campuses, my university at Arecibo, University at Mayagüez, to achieve this.
It's a pretty fantastic thing that it took so many people,
many people,
to make this happen, but it's finally happened, which is incredible. And to have one here in Puerto Rico is it's an experience, and I can't wait to see your collaboration with this project. And also about the collaboration side, so I think that you're going to be involved in some of the analysis and with some students who are going to be helping you with that here.
Yeah, definitely. I am interested in many things about having an optical instrument, not only about SETI, but also if we have any additional applications, like in meteorology, meteors, or any other transient optical events. So we will try to involve students and professors here from Puerto Rico that we have this, and tell them that we have this instrument, and if they have new ideas, just to how to interact with the data in a different way also. So we will take advantage as much as possible.
I love that. And this is truly it's a worldwide, it's becoming a worldwide endeavor to do this, and involving so many different people in different career phases. It's really opening a lot of doors, which is incredible. But speaking of students, we actually had one of your students who was helping us to install the instruments yesterday, so that they can learn and come and check on the instruments to do maintenance, or mess with anything that is, causing any unknown issues, or just check on the instruments in general. And I actually wanted to show everybody. We have a time lapse of us installing the instruments with the Abel student Francisco. This was yesterday. We had already gotten the instruments themselves up on the roof with the help of the Astronomical Society. So
of the Caribbean.
Yes. So thank you to Rafael and Martin and Evans for helping us. That was the main work, was to get the instruments up on the roof. And then this was us installing and connecting everything and making sure that the instruments were aligned so that they can look at the correct part of the sky. And oh, I have another great picture here. So this was with the Astronomical Society of the Caribbean, our volunteers who helped us, as well as Franck Marchis, Elliot Gillum, and us. Yesterday, the day before, it's all blending together now because it's been so much fun. So yeah, I'm really excited that you're going to be involved in the LaserSETI project. And I know that there's a little bit of synergy between LaserSETI and some stuff that you're doing. So this kind of all-sky survey with the optical, I believe you have something similar in the works, but in a different wavelength regime.
Yeah, we are working and in radio astronomy, trying to do an all-sky survey. For radio astronomy, we don't have the problem of the weather. It could be, we could be having a thunderstorm, and that would be fine to do observations. But to achieve that with telescope is very hard, because big telescopes are always focusing in a particular region of the sky. They are busy with many requests from astronomers everywhere. But to have an all-sky observation in radio, that's very hard. And we will try to do is create these small telescope systems that people could buy and join in a network. So it has a rich component, but it also has a science component. So we can be monitoring all skies in the radio spectrum. And we will start from Puerto Rico, and then other people will join through the world, eventually having a network. And the good thing, so we have the connection that if we find and we see a signal in the optical, we can check in the radio. Or otherwise. If there is a component, some astronomical events have, like I say, supernovas. You see the flash of light, but you also see a radio signal, not necessarily at the same time. That's quite interesting. So there's too much to do.
Exactly. And they all last for different amounts of time as well. So to be able to confirm in different wavelengths with different instruments is going to be really useful.
That makes the signals real.
Exactly. Not just a figment of our imagination. I'm really excited to see what happens with that. And in that idea of radio astronomy, you actually have some really big news that's come out recently. Your team has done a lot of work on the WOW signal. So do you want to give us a brief overview of what the WOW signal was? And we'll talk about your research.
The WOW signal is an icon now in SETI. It's a signal received by the Big Ear telescope in August 1977. This telescope was actually doing a SETI project, and they detected the signal that we were looking for. The problem was that it was just one signal, but it was very distinct from everything else. So it was easy to recognize at that time that doesn't look like some radio interference. So it got at the attention slowly of the community for decades and until today. So now we are working on this, checking that data, the original data from that signal, and trying to understand it. And we started this project the original idea was that we were looking for similar signals in the Arecibo data. We have some archive Arecibo data. So you will see Arecibo will live forever because we will keep looking through the data. And so we started reanalyzing the data, but now looking for WOW-like signals. And we were surprised that we found similar signals, but not necessarily, they're similar, but not necessarily the same source. And that kind of idea, these were hydrogen clouds that were emitting, some small hydrogen cloud can emit this signal that look like the WOW signal, but they are constant. It's not like the WOW that was a flash in the moment and they just disappear when you observe later, there's not there. So the clouds are constant. So they found these signals, and we observed those signals and just got interested us in of these observations. And yes.
That's fantastic. So when I was reading your study, I was seeing that this is kind of the first reanalysis of that old data, but now using modern signal processing techniques. So how are those techniques different than the techniques that were used at the time when the WOW signal was actually discovered in the 1970s?
I think this is the most amazing part of this work in terms of connecting not only the instrument, the history of how the back then things were done, how we do things now. Most of the data during that time were archived in papers. And
as you can see, this is the WOW signal on paper.
Just one page, but there are thousands of those pages. And so it was a very different way to analyze the data. And now we have the capability of also compare every signal that they have in those data.
Right.
Some signals they even skip it because they thought maybe there was some interference. But we now know what they were, those signals.
Right.
So we can compare with modern measurements, and that's the advantage. We have so many tools right now in processing, archive of the data, space, and analysis to compare this, analyze the data in different ways. That is amazing.
That's fantastic. Yeah, this is definitely not something that you would see nowadays, this readout from the telescope on paper. And you can see where the scientist at the time saw that there was this huge, intense signal coming through the telescope, and he circled it and put WOW. And that's why it's called the WOW signal. But we wouldn't have something like that. We wouldn't have something like that today. So let me just take that off real quick, because I wanted to ask you another question. So in your new study, you found a new, more precise location for the signal, which hasn't been done to this precision before, especially I think because the signal was only received in one horn of the telescope. So it's been hard to identify where it came from. Now you found that more precise location. So where is it, and how did you find that?
Yes. So when we initially published a potential explanation for this WOW signal, that got the attention of the actual astronomers that were detected the WOW signal in the 70s. So and they gave us the data. And we went through that data and looked for sources, known sources, radio sources that we have been observed today with modern methods. And we use those sources for two purposes. First, to find and correct the position of the telescope.
Okay.
So it's very hard to make sure that a telescope is pointing in the right direction, but just by the geography. So once you find known signals in the sky, you can compensate, and the more the better. So that's why having this data and having these known sources, we were able to correct the position. Once we correct the position, we compare that position with the many sources.
Okay.
And it was amazing. The telescope was working fine. It was just a little bit shift in a position.
Okay.
So, and it was a small shift in seconds, but looking at the sky, that's a lot.
So you were able to find kind of this inherent shift from the instrument and then correct for that, and that's how you got this more precise location.
Yes.
Okay.
That was the reason. That was the plan.
Very cool.
And it worked.
That's incredible, especially for something like that to have happened in the 70s, and just now we're getting that more precise location and discovering new things about this signal, which has kind of been a mystery for a while. That's incredible. So I know also in your paper as well, you talk about some similar signals that you saw in data from the Big Ear telescope, and you called them WOW 2 and WOW 3. Like thing 1 and thing 2. I love it. But what are these signals that are similar to the WOW signal but also different?
Yes. Okay. The interesting thing is that when we did our observation in Arecibo, we detected these signals, natural emission from hydrogen clouds.
Okay.
So they are persistent, constant. Every time you look at them, you see the same intensity. But they are narrowband because these clouds are small. Usually you have a lot of hydrogen, and this because it's moving at different speed, you have these broad lines. And so, but to have a narrowband, you have to have a very compact cloud.
Okay.
With the speed of all the molecules in the cloud about the
sense.
same. So that's how we got interested, because it's similar.
Okay.
So we saw that in the data. That's something that nobody probably seen before, because everybody knew about the WOW page that you already showed. But there are thousands of pages like that. That once we got the interest of the scientists that observed with the big ear, just provided all that data, and we found many instances where you see these hydrogen clouds producing a signal like the WOW signal, but much less intense. And here you can see that this is one in particular, and you see that the numbers in the background is 1, 2, 3, but you see going to 5 or 6 in a line, which is similar to the WOW signal, but the WOW signal was so intense that went to letters. Letters means higher numbers. So this is proof that they're similar, not necessarily the same phenomena, but they produce similar signals. And we confirm that those indications, like what we call WOW 2 or 3, are regions of hydrogen clouds. So we have also in that paper the actual image of the hydrogen cloud, and it's small, so you can compare. Yes, and once we calibrate the position of those signals, we just put the coordinates, because we have a calibration already.
Right.
So when we put the coordinates and check in the spectrum, it tells you that the hydrogen distribution right in the middle of those clouds. They're not that common, but we see them and in many. And this is just one day, and the next day they show up, and then months later, because they're constant emission. So what we think is that these clouds got somehow brighter. And that's the WOW signal.
Because these signals that we're seeing, so this is WOW 2, I believe. So these signals are transient in the way that they don't last forever. They last for a short amount of time, but they last for much longer than the original WOW signal. So there's something a little bit different happening.
These ones are persistent. They're decades. You will see them. They are natural emission of hydrogen. So the difference in the WOW signal is some astrophysical process that will brighten them up for a moment. And a moment, I mean hours, not necessarily days, because once the WOW signal was detected, it was observed 48 hours, 2 days after, and it was not there anymore. So, oops, what happened there?
Exactly. That's really cool. I love that there's now some things that we can actually do to study similar phenomena and then extrapolate. I mean, that's what science is. I see some new people who are joining us. Let's just say hi to them really quickly. From Atlanta, from Boulder, Colorado, in the States. Welcome. We've got some questions, so maybe we can take those a little bit in the end. Hello from Germany. Hi, everybody. We're talking about Dr. Abel Méndez's new paper on the WOW signal. And I think I have a couple of more questions for you. In your paper, you found that the signal intensity of the WOW signal, the original WOW signal, was actually 4 times greater than previous measurements. So how did you come up with that intensity? And what would cause the discrepancy between your new measurements and the previous studies?
Okay, yes. Previous measurements and the last measurement of the intensity of the WOW signal was in the 90s. Was it the 90s? But actually, Jerry Eman, the one person that wrote WOW, he did a reanalysis back then. And when he did his analysis, he considered the optimal condition of the telescope working.
Right.
So that's a baseline. So that's good. But the problem is, once we got all the papers with all the data before, the hours before and after the WOW signal, we saw something interesting. that the noise levels were changing because of, in fact, the Webb signal is close to the galactic center, and because it's close to the galactic center, it has more noise, natural noises. So that made that the noise was high at that moment. So, if, for example, a weaker signal will be buried in that noise. So it has to be very strong. And that's why when we realize what the noise levels through all the day, so you needed all the data from the whole
all
day.
All that archival data.
Yes,
yes. Got it.
And to realize the actual noise levels, not the optimal noise levels.
Right. Optimal and actual can sometimes be very different in science.
Yes, so that's why we were able to point, and using some calibrators, also noise radio source, close to the time of the Webb detection, before and after, to tell exactly what was not exactly, this is a minimum, so it could be much stronger. What would be the minimum intensity of the Webb signal, and that's why it's a larger value, and that inspired us to many things.
That's really interesting, especially after all this time. This is it's incredible to find out new things.
Yeah, we were surprised. That was not our plan.
Not the point.
Not the
paper,
point.
Right.
It was more like now we have data. Let's revise everything just to understand better. Maybe one thing that we started was we were scared because maybe we can find out now that it was radio interference.
Right.
So we would try that first. We tried to compare the signal, and even that the noise levels was higher, but there's constant.
Okay.
And we see through the whole data that there is nothing like the Webb signal. Like, for example, if you have a random radio noise, it could be higher, lower, and they produce any signal, and by coincidence, one signal will do. It's not like that.
Okay.
So we look at all the sources and concluded that it's very unlikely that this was something related to a radio interference.
So then that means that it's most likely to be astrophysical.
Astrophysical, something from the sky.
Okay, yes.
Something from the sky.
And I think that you also had a study last year that kind of talked about some of this. So when we say it's most likely not radio interference and likely to be astrophysical in origin, what could those origins be? So you were talking about the clouds before. So how would that relate to produce something with the intensity of the wow signal? Yes.
So once we got the idea, because of the clouds, that they can produce these narrow bands, so we have to invoke a astrophysical process just to make them brighter momentarily. And that's the big deal, because that's very hard to happen. And luckily, we have an idea that probably some laser process that's similar to laser, but in radio, so could make these clouds brighter. But how? But we also find that other scientists already were proposing that these hydrogen clouds could be enhanced by another process similar to masers. It's another process, but it's called superradiance. So at least there was a maser flare or a superradiance. There are two different processes, but they actually will make a hydrogen cloud brighter for a moment. Especially superradiance, it will be shorter in time. It more fix the data. So we have these two processes, and they were proposed in theory before, but they were never connected at all to the Webb signal.
All right.
So you made the connection. So we have here the theory, we have here the data. Okay, this fix everyone. And that's the important thing. All the observation parameters of the Webb signal, the duration, the intensity, the narrowband, they can be explained with this astrophysical phenomena. But the problem is that we have just one observation.
So it's not quite enough to decide for certain what that astrophysical process is with only that single 72-second long signal. So on that topic, when you're thinking about all of the things that the wow signal could be, what would you want people to take away from this new study and what it could mean? And then we'll take some questions.
Yes, this is significant. This is a very interesting signal. No matter the explanation, you should say wow. Because even if we find out later on that by some way it was a radio interference, we were struggling how, of all the possibilities, a random radio interference could produce something like this.
Right.
It would be amazing. It was something to be wow. We would say wow, definitely.
Yeah,
so
it would still be wow.
And that will be something important because
people are saying wow in the chat.
Good. So that would be something, to care about when we explore signal. We learn a lot. But is that something astrophysical? Then it will be validation of these people that has been proposing mechanisms for the enhance of the hydrogen clouds. And it will be confirmation a new astrophysical phenomenon.
Yeah.
Something that happened like pulsars in 1967 or the fast radio bursts in 2007. When they were detected, they were associated with aliens.
Right.
But now we know they're astrophysical phenomena. So we're still struggling with the wow signal. Is that the case? That will be a new astrophysical phenomena now, proof for that. And is then aliens? We're done.
That's also wow. That's also very exciting. Yes,
it's
absolutely. Wow. So yeah, thank you so much. We're nearing towards the end. Let's check on our upstairs really quickly. How are we doing? All right. It looks, I don't think it's going to rain, so maybe we'll be able to go up there here in a moment. But those are our 3 stations looking fine. I wanted to take a couple of questions from the audience. So let's see. Let's see. Isato Sar says, could multi-wavelength correlation reveal if the wow signal had counterparts outside of the 1.4 gigahertz band?
Thank you, Isato Sar, for the question. Yes, that's something we thought about. And our team is looking in archive data for also is the wow signal had an optical counterpart. So we looked through the archive of data from different telescopes through the world in the 70s, just month before, month after, and to see if there is any indication. We hasn't found none. In general, our idea and our explanation does not need, this is a radio signal, it shouldn't have an optical counterpart.
Right.
But anyway, we try to cover all the bases and explore all the possibilities. And that's one thing that we consider. Thank you for the question.
Yeah, that was a really great question. Let's take one more, and then I saw a LaserSETI question really quickly. So Mikhail Larson asked, is the frequency where the wow signal originated more monitored than other frequencies?
Yes, in terms of astronomy, this is a protected frequency range. And so it's used and it's observed a lot by astronomers. So you might think, okay, so why we haven't detected a wow signal many times before? The problem is that if this is a rare event, and we calculate this, let's say the event is just once per day, it would take hundreds of years of 100 telescopes just by chance to get a signal, assuming they are randomly exploring the sky.
Right.
So we don't have, especially all telescopes in the world covering all the sky. So we are missing. That's why I can compare that
so you're working on that though.
Yes. Yes, with a small telescope. The fast radio bursts, there are thousands per day. And we discovered them in 2007. And the ones in the signal before, they were ignored that this has to be some R5.
So, I just wanted to tell people in case they didn't know, can you answer why it's a protected frequency?
Really because that's a frequency important for radio astronomy. Hydrogen emit in that frequency. And it's important because the distribution of hydrogen in the galaxy, that's something that you can see in the radio spectrum. Also to know the shape and structure of our galaxy. It go across not only of the atmosphere, but across clouds of dust in space. So you can have a good indication of what the structure of our galaxy is.
Right.
It's important in many ways.
That is, so I want to see if we can go up to the roof here in a second.
Mm-hmm.
So I'm going to move on to a couple LaserSETI questions, but thank you so much for explaining your research, because this is truly incredible to have you here, to be in Puerto Rico, to have you as a part of LaserSETI, and also talk to you about your research that's really starting to narrow down the WOW signals. So just
I am very grateful of all the people in Puerto Rico that help us, our team, our students, and also especially to the SETI Institute.
He's even representing with his shirt right now.
Yes.
Yeah, exactly. So let me just take a couple of questions from Ron Schneider. So he asked why he thought LaserSETI was just one unit per location. And we did. You are correct. Thank you for noticing. Yes, there are 3 different instruments at this location. So the important thing about LaserSETI is not necessarily that there are only 2 instruments. We do want to have them perpendicular to each other. We can see multiple parts of the sky and also overlap. But in this particular location, there's plenty of room to have those 3 instruments because of this awesome rooftop of the Department of Marine Sciences. But also, this is the right location for us to be in to have enough instruments to overlap multiple other LaserSETI observatories. So not only are these stations partially overlapping our Sedona fields of view in Sedona, Arizona, but they will also be overlapping the next LaserSETI location. So that's why there's 3 instruments here, is because it was possible and because this was a great location to be able to actually accomplish the overlap that we need. And we need overlap because, just like you were talking about, we had the WOW signal and it was just one signal and we were never able to see it in any other data. LaserSETI, if we see a laser pulse, we want to be able to confirm it with other telescopes on that part of the sky. So thank you so much for the questions. Somebody also just asked, let me just really quickly, where can we keep up with the works you folks are doing? Thank you for your question. You can go on laserseti.net. You can follow LaserSETI on Facebook and Instagram. What about you, Abel?
Yes, you can follow our work in our website, phl.upr.edu/wow. We have there our recent papers and data for all people that want to get and look at the data themselves. It's there.
Awesome. Cool. Yeah, we hope that you guys will follow along with us. So, all right, I think that we're nearing the end of our time. I saw one more question I want to really, really quickly answer on LaserSETI. Let me see if I can find it really quickly. Oh, our friend asked the question that I just answered. So that's perfect. Thank you, Isato. All right, so let's actually do something that we haven't really done before. We're about to say goodbye to you all. Thank you so much for attending from all over the world. Guadalupe, Northern California, so many people. We're actually going to try to run up there to the rooftop and say goodbye to everybody. So we'll see if this works. Now you know that this is a live stream. We're doing this in real time. But let's see if we can go do it and we'll say goodbye to y'all. Thank you so much. All right, I'm going to turn off my camera and you're gonna see the LaserSETI stations and then we'll pop up in that screen. All right, let's go up. Not sure if you can hear me. Bye, everyone. Beautiful. Yes. Thank you so much for watching, everyone. Have a wonderful rest of your day. Thanks for attending this LaserSETI Live with myself, Lauren Sgro, and Dr. Abel Méndez. And keep looking up.